let's jump straight into the topic. Guys, you know, we're Canadian, we're in Canada. I myself have never seen snow before I arrived here 15 years ago. But for me, snow is not really fun. I'm not skiing, I'm not skating. I don't enjoy the -30 much. Uh, as an engineer, snow is a load. Look at the picture and you will see lots of snow accumulation. And I guess if we do not design the roof in this picture to withstand the snow load, I guess this structure or building will simply fail. Now, here is our snow equation. So what you see on the screen is a snow equation, which comes from the Alberta Building Code 2019, and the close number is 4.1.6. Now, what I'm going to do today is I'm going to show you the equation, show you all the parameters, and we have lots of discussion about every individual parameter. Guys, let's start. So the S to the left, which I'm going to point out right now, this S over here is your snow load. And it is going to be expressed as KBA, kilo Newton per meter square. So weight per unit area. And by the way, so you know, the one on the left is our final target. Our final target is to find the snow on the roof. Okay. Now, there are so many parameters on the right side here. And as I said, I'm going to go one by one. Okay. Every one of those needs discussion. Now, I'm going to read the equation for you. It starts here on this side with something called IS. And I already included the definition or the name of every parameter or factor in the equation. So I sub S, it is simply representing the importance factor for snow, load. Again, every one of those will require a discussion. But the importance factor is simply tells us how important our structure is. Next to the importance factor, there is something called SS, and SS is a 1 in 50 year ground snow load in KBA. You guys can see it. I know so far you've seen 2S, and I want to explain the difference between them. So the S simply is on the roof, while the SS is the ground snow, which means on the ground. Because roof will get a little bit different snow based on so many factors. So the SS, as I said, it's the 1 in 50 year. This is a probability level, which means this snow amount will happen only once every 50 years, Now, following the SS, there are 4 different parameters, which is C sub B, and then C sub W, C sub S, and C sub A. And those are modification factor based on several variable. C sub B, it's something called the basic snow load factor. C sub W, it's wind exposure factor. And C sub S, it's called slope factor. And then C sub A, it's accumulation factor. And look at this place. So every one of those factors are explained in more details in a later sentence. For example, C sub B, we need to refer to sentence number 2. For C sub W, we have to read statement number 3 and 4. For C sub S, we need to read 3 statements, 5, 6, and 7. And then for the accumulation, we need to refer to sentence number 8. The last element in my equation here is S sub R, and S sub R, again, it's 1 in 50 probability, so it will happen once every 50 years. Something called associated rain. So when it snows, you get a little bit of, I would say moist, not really rain, a moist. So this is the moist component of your snow. It's called or referred to as S sub R. Again, maybe by now you know very, very little, but I promise you at the end, you will see and know a lot about every individual factor or element in this equation. So guys, let's go ahead and explain for you the meaning of every individual factor and how do we find this factor. So guys, I'm going to start here with something called IS. If you remember, IS stands for importance factor. And because it refers to the snow, then it gets the sub uh, of S. In wind, I guess probably by now, Corwin already covered this topic. And in wind, you will see a very, very similar, I would say it's the exact thing. It is called I sub W. It's an importance factor for wind. Here, we're doing importance factor for snow. So guys, let me explain for you that not really all our structures, we deal with them with the same amount of care. I know some of you will say, Tahir, early on, like 2 weeks ago, you came to the class and said, you know what? We never design a structure to fail. We design structure to stay. But the thing is, when does it stay? In normal situation or in abnormal situation? I'm going to explain in details. Now, guys, let me ask you. Now, let's say we have a huge snowstorm, a huge snowstorm. Now, what do you think? Which building should I deal with in my design very, very carefully? A hospital, or your house? Maybe some of you will say, you know what, you need to design my house to be very, very strong and withstand this snowstorm. Okay. Yeah, all of us, we love our houses, but from engineer perspective, the house is normal importance. If something happened to your house, as long as you're safe, your insurance company can build it again for you. However, things like hospital, in case of big event or like storm, windstorm or snowstorm, then in this case we don't really accept that the hospital will collapse in a snowstorm. In this case, what do you think if the hospital collapse? People the if the like the if you have somebody injured, so will go nowhere. By the same token, think about police station. By the same token, think about fire hall. Okay, so there are some structures that we simply want them to stay intact in event of snowstorm. Now, if you want to know better, please go ahead and look at the table. So I'm going to let you guys look at the table. I want to say something before I continue. If you guys remember, I uploaded a file to the D2L last class, and I said not completed or incomplete. I have done some work and I finished it. So by now, you should be able to download the PDF of this presentation from your D2L. So if you can go ahead right now and do that, go to your D2L and download this PDF file. I want all of you guys to simply read the table. I'll give you 2 minutes. I'm not asking you to memorize, what's in the table. I want you to get a sense of the structure of the table. Why do we classify some structures as low or normal or high importance or post-disaster structure? The examples on the first column will tell you how, and hopefully this will convince you that as engineer or designer, we treat the design of individual structure based on the importance of the structure. So a couple of minutes, I'll come back or talk again 1:13. Okay, guys, now I have a question for you. Since by now probably you have an idea of the table, and let me ask you one more time. If you were to design a house, just a residential house, okay? Now, which you think, what is the importance category when designing a house? Is it low, normal, high importance, or post disaster? I Harjut.
Normal, normal.
Okay, thank you, sir. So somebody else, please. Please, typing into the chat is typing into the chat is kind of distracting me. So please try to avoid the typing in the chat. However, I can simply give Harjut. So I have 1 mark for Harjut here, and I also have 1 mark for Colby and Ariana. So thank you so much for contribution. Just be patient, please. So yeah. So yes, of course. So you can see, although our houses are very important for us, but from engineering perspective, we design them as normal importance. However, things look at the post disaster, and you will understand hospitals, blood banks, power generating station, water treatment facility, sewage treatment facilities. All those you guys need to think about it. What happens is if you have a windstorm or snowstorm, and simply one of those structure in a post disaster simply collapses, then that's a disaster itself. Okay, so those structures we deal them as a post disaster. High importance are as explained, the table explains, it says buildings that are likely to be used as post-disaster shelters, including building whose primary use is elementary, middle, secondary school, and then community center. Guys, I remember back in 2013, I'm not sure if you remember this time. So 2013, this was 7 years ago. Calgary flooded, and it was really bad, and lots of houses they were flooded. I remember that time, people they have no place to stay, and they went to or the government assigned the leisure center in the southwest called Southland Leisure Center as a shelter for those people. Okay, so you think about those places are as a shelter. I would say it will be included in the same category, although it's not really a high school or mid school, elementary school, but probably people they will take shelter when if there is a like a snow an event of a seismic or windstorm or snowstorm. Okay. Now, probably the last one, which is low importance, this one probably will not, you need to probably get more information. So what exactly do we think as low importance? So in the table, it's trying to help give the designer a help, and it says buildings that represent a low direct or indirect hazard to human life in the event of failure, including low human occupancy, and again, the bottom line is if this building is to collapse, in case it is to collapse, then it's not going to cause any fatality. Guys, I have a very like kind of a good example for that, which is like animal shelters, or hay barn. Those are places we put the animals, and probably a single person will go once or twice a day to feed the animals. And probably when this structure fails, nobody's going to die. Okay, so we those and typically agricultural building for animals, we deal with them as low importance. Okay. Uh, and anything else which is not post disaster, which is not high importance, which is not low importance, anything else it becomes as normal importance. This includes office building, includes my house, your house, includes anything that is not post disaster or high or low. It is normal importance. Okay, now how this will affect my design. So guys, you can see even right now, by now, even if we say, Here is a hospital, a Foot Hills hospital. So how this, like, yes, of course, it is post-disaster, but how this simply affects my design, that this will be answered in the next slide. So once you decide the importance category from this table, then you go to the next slide or the next table in the code, and simply it tells you, here is your magnification factor. Remember, post-disaster, we need them to stay in the event. So you need to add more care. In terms of mathematics, more care, it means a number more than one. So instead of designing the building for 100% of the load, we design the building for 125%. So we have extra 25 care on 25% care on this building. So, okay, so here is another table from the code. And this table now is not by writing, it's not text, it is number, which means, please read with me. So if you're designing a hospital, and this hospital, we know it is post-disaster, then when you design, simply you multiply all the loads times 1.25. It means add extra 25% here in your design. Okay, how about if I design a high school or elementary or mid school, then you can see the number on the top because it's a high importance. Then we add only 15% extra care. It means I multiply my number by 1.15. Normal importance, it means they are normal. It means I'm not going to add or subtract. I'll just use the load as calculated. Finally, if you have a low importance category, like agricultural building for animals, then in this case, we multiply the load by 80%, like 0.8. And remember, those numbers are ultimate limit state. Look at the header of the table, ultimate limit state. When we design the element in the SLS, which is, for example, checking how much deflection, then what is my importance factor? Then we multiply times 0.9. And I know some of you will say, hey, Tahir, how come? So which means when I estimate my deflection for a beam, I should use the load multiply, the snow load multiply times 0.9. It means less than the snow load. Yes, because remember, snow load, it happens like probably a few months of the year. It's not really the entire year, and it's going to be overkill. If I design the roof for the 100% of the snow, I'm referring to the deflection, guys, as I said, you have exactly the same thing for wind, and I bet you by now you know the I sub W. If you guys remember the number for the SLS for I sub W, so those will be the same for the wind, but those will be 0.75. And some of you will ask, how come 75%? So when I check a beam for deflection under wind, I use only 75% of the wind. It makes sense because if the wind will blow only for a few seconds, so the wind will gusset for a few seconds, and it's overkill if you design or check the deflection based on 100% of your wind load. So we use only 70%, 75% of that. Anyway, watch this. So by now, you know that the I sub S, it is an importance factor. You know how to find it. It is two steps. You go to the table, find the category, and after you know the category, you go to this table and find the value of the I sub S. Remember, I sub S is unitless. So I sub S has no units. It's just a factor, okay? Normal is 100%. Post-disaster is 125%, and so on and so forth. Now, here is an exercise for you. And we already answered this one. So I was asking for you guys to find for me the importance factor for your house. So this is done already. So let me ask you next. What do you think about the importance factor for Powerhouse in Foot Hills Hospital? You guys know that hospitals, they have their own kind of reserve power station to generate power in case of they don't have power. Okay, so I'm asking you, Powerhouse in Foot Hills Hospital, when we design, what should be the importance category? Diego.
It has to be high post-disaster importance because you don't want to run out of power in a hospital.
For sure, sir. For sure. So designing the put your hands, please. Designing the powerhouse in a foothills hospital. Then it is a post disaster. Now let's look at warehouse. Warehouse. A warehouse. So guys, a warehouse, typically it's a place for storage where or maybe sometimes like a shop or something where we store, for example, like tires and furniture. Those are what called warehouses. Okay. I have Ayushman. Ayushman.
Okay, I raised it for the other question, sorry.
Oh, no worries. So okay, next is Brody.
Low.
So warehouses are low.
Yeah, for storage, it's mainly storage.
It's not like warehouses, as I said, uh, not only a storage, like look at IKEA. IKEA as a warehouse. So there are some people going with some cranes picking the furniture and they work the entire day. It's not like a place where you store something and then you come like once you pick it and run. No, it's not like a feeding an animal for 5-10 minutes and then go. The people in the warehouse, they stay for the entire day. They work in the warehouse for the entire day. So let's go with Sunny.
It's a kind of mixed one, because as I can see, so warehouse has low human occupancy, so it should be in the a low one, but the warehouses could have the hazardous substance and all this stuff, so it could be in the high one as well. So I think it better lies in the high one.
Yeah, if you store in the warehouse explosive material, yes, I agree. If this warehouse to store explosive material or hazardous material, of course, yes. Okay. But in general, warehouses, without being very specific to explosive material, in this case, warehouses, they fall into normal. I'll just give you one mark here. Okay, thank you. I think high school is very, very clear. We don't have to answer this one because high school very explicit in the table, and high school is simply high importance. Okay, guys, next is please put your hands down. Thank you. Okay, so guys, the next part is I'm gonna probably revisit my equation one more time. So far we covered IS. So the next is actually we will cover two together on the same discussion. So we have S sub S and S sub R. And to remind you, S sub S is the ground snow, like how much snow will fall onto the ground. And then S sub R, it is simply the associated moist or rain. Okay, guys, simply this is a climatic information. It is function of the geographic location. Um, I think if you live in Canada here for some time, probably you'll know that. In Calgary here, although I know it's very cold and I know it's just like sometimes drops to -30 or -40, but so you know, we don't get here so much snow. So you know, if you think that's too much, I think you should go somewhere else. Uh, there are some other areas, they get lots of snow. If you go to the mountains, so if you go to the mountainside, in the mountain, it is not as cold, but it's super, there are lots of snow. Okay. I remember I went to, or my friend told me that he went to Waterton in winter. So Waterton is a very nice place. It's like a 3 hours drive from Calgary to the south, to the border with the USA. And there's a very nice lake over there. However, one of my friends went in winter, not in summer, and the snow simply covers the houses. So the houses are covered by snow. So it's not really a 1 foot or 2 feet. It's just like 10 feet or maybe more than 15 feet of snow. So my point here, guys, is the snow is function of where or the geographic location. The snow is function of the geographic location. So that's why please look at the next slide. So the next slide here, in the National Building Code or the Alberta Building Code, they try to give some information for the designer and for the engineers to help them with these numbers. Okay. Now, guys, I think we've been collecting climatic information now for over 100 years, even more than 100 years, for sure. And so what happened, we measure all 24/7, every day, everywhere in Canada. We have a like climate station or weather station where we measure temperature, pressure, rain, you name it, including the snow, I guess you've seen the same table with Corwin. So Corwin will look at the same table, but will pick different column. So because with Corwin, he is probably teaching you the wind, and the wind you can see in my slide here. The wind are it is just the column to the right. I just kind of box in red here the column that we will use in my class. So this box here is simply the SS in the first column and then SR in the second column. You can see there are so many geographic locations, like for example, Airdrie, Banff, and other places in Alberta. So I picked this from the Alberta Building Code. In the National Building Code, they have way more than that because simply it is Canada-wide. So almost any city and town in Canada, we have the information for the city or the town. Okay. So guys, if we focus on Calgary, so I kind of mark horizontal box here in red as well, which is for Calgary. And if you want to know what is the snow, the SS and SR for Calgary, here we go. So it's the intersection between the two columns and the Calgary row. So the numbers are 1.1 and 0.1. Those numbers I remember them by heart because I have done so many like design in Calgary. So I don't have to even to look at this table. I know in Calgary it is 1.1 and 0.1. So SS is 1.1, S sub R is equal to 0.1. Something very important I want to mention right now is those are not unitless. The SS and SR, those are snow load, which mean they have units, and then it's our KBA. So you can see here, look at the table header, it says KBA. One more thing, I need to remind you that the probability of those number, it's 1/50. So look at the number here, look at the top. Look at the top of your the top of the column. It says snow load KBA 1/50, which means this snow intensity will happen once every 50 years. And guys, I know some of you will ask why 50, what's specific about 50 years? Because we design our building, in most of the building, we design them for 50 years. I know some houses in Calgary, they stay more than 50 years. Some of them, we have houses, they are 100 years old. But as a designer, as an engineer, I'm responsible for my design or this building to stay intact for the next 50 years, okay? Not every structure is designed for 50 years. There are some other structures which is, we don't have the luxury to build them every 50 years. Like for example, bridges. So some bridges, they are designed to 150 years or 200 years even. So the bridge will be designed to stay 150 or 200 years, okay? Looks like there are some questions. So I'm gonna get the questions, okay? So let's start with Jelly.
Yeah, sir. The indication of the SR 0.1, does it mean it's too low because we don't have much rain in Calgary?
As I said, it's not rain. I can kind of confirm that it's not rain. So not the rain that you see in summer. Okay, so next class or probably next week, somewhere next week, I'm going to explain the rain load. In that case, it's rain happening in summer. But this 0.1, it is a little bit component, comes with the snow. I call it moist. I don't want to call it rain, but the code says rain. So this is a small, yes, you're right. It's kind of 10% of the snow would be kind of a wet snow, if you will. Okay. Next is Diego.
So the 1/50 that you were saying, that's it. That's the probability or the maximum over the last 50 years.
It's a probability level that this probability, it means this amount 1.1 will happen once every 50 years.
Okay.
Guys, since Diego asked this question, those numbers are not fixed. So those numbers are not fixed. Remember, we're collecting like data every day, 24/7, which means probably maybe in 10 years and 20 years, those numbers will change. Especially right now, we're going into global warming, and you can see lots of weather disaster all over the globe. I bet you those numbers will change in few years. Okay, so that's why we need to use the latest code. Okay. So again, before I leave this, I want to emphasize that those numbers, the units are kBA. Okay, unlike the I sub S. I sub S has no units. One thing maybe some of you will ask, okay, Tahir, what if I'm designing like a structure in somewhere where I cannot find this place on that table? What can I do? Like, let's say you go in a very small town, you're designing like a small building there or a building over there, and you don't know like what is the SS and SR. I myself have been into this situation before, and I had to call the local municipality to ask them about the snow load. And if they don't know, then what you need to do is just use Google and find the nearest place on this table, which takes some time to find the nearest place from Google Map, and simply kind of interpolate to come up with SS and SR. Again, that's a due diligence, which means if I do that, that's all I need to do to do my due diligence to find the best number for SS and SR. Okay. All I'm saying here, also you have to be careful. Even if you have a small town, let's say 20 or 30 kilometers away from this town, however, this town under consideration is close to the mountain, be careful. Coming close to the mountain will increase the snow significantly. Okay, even you have another town a few kilometers away from the town under consideration. Okay, now let's move on to the next one, and I'll remind you back. So I'm going to go back to my snow equation. So far, guys, we know the meaning of I sub S. We know the SS and SR. We know how to estimate them. And I want to prepare you guys. I know that so far everything for the probably this hour, the next hour will be very theoretical. We're just saying something, and just be patient. In today's class, I'm going to give you examples by numbers, so you understand the whole process. But I'm going to go right now through individual elements one by one until we finish. Then we give you a numerical example. Okay, so you can see here the next element is called C sub B. Okay, so the next element is called C sub B, and you can see all of them, they are C's. So C sub B, C sub W, sub S, sub A, and all of them, those are modification factor for the ground snow because of a good reason. Okay, watch me, please. So the next one is something called C sub B, and it's here, and it is unitless. I have to emphasize that this is unitless. It has no units. And so this number, the code was referring us to statement number 2, and I kind of a snapshot statement number 2 from the code. So statement number 2 from the code, it says the basic roof snow load factor C sub B shall be determined as follows. There are two cases. Number I, CB equal to 0.8. You can see kind of very simple. CB equals to 0.8. Now, what is the 0.8? Like, or when can I use the 0.8? It says here for L sub C equal or less 70 divided by C sub W squared. Okay, please be patient. Okay, don't get so anxious about it. Okay, everything here, I will try my best to make it simple. Okay, so C sub B equal to 0.8 for L sub C less than C70 over CW squared. Okay, now let's go ahead first and know and understand the L sub C. So under that, under here, there is something called, it says where L sub C, it is the characteristic length of the upper or lower roof as defined as 2W minus W squared over L. Okay, 2W minus W squared over L. So guys, where W is a smaller dimension of your roof and L is a longer dimension of the roof, okay? So basically, if you have a roof which dimensions, like let's make it simple, let's say that our roof is a rectangular roof with a longer dimension L and a shorter dimension W. So the LC is not the average, is something called is something like an average, and there is an equation to estimate it, which is 2W so minus W squared over L. Okay. Probably we can take an example right now if you wish. So let's say I have a roof and this roof is, let's say, 20 meter by 15 meter. Okay. If I have a roof 20 meter length and then 15 meter wide. Okay. How do we estimate L sub C? So L sub C equal 2 multiplied by 15, because W is the smaller dimension, minus 15 squared divided by 20. Please go ahead and do that on your own. Do that on your own, please. Okay, if you know the answer, if you got the answer, please type it in the chat for a mark. I'm going to take the first 3. That's enough. Stop. That's enough. Okay, so you guys, you're right. 3 of you guys. So we have Merin and we have Siham and we have Brody. Let me give them a couple of marks here. We have Siham, so 2. And then we have Brody, 2. And then we have Merin. So Merin, thank you, Merin, for 2. Okay, that is correct. And you can see we are able to find L sub C. So I'm asking you right now, for this kind of roof, okay, what do you think? So the L sub C is equal to 18.75. And I know in the equation it says 70. If this number is less than 70 over CW squared, and I know some of you will say, Tahir, so far you didn't teach us the meaning of C sub W. In shortly, probably in a couple of minutes, we'll go through C sub W, and you will see that C sub W in all our cases we will use as 1, okay, as 1. So please look at this equation right now as if C sub W equal to 1. And if C sub W equal to 1, life becomes so simple, because simply we use C sub B equal to 0.8 whenever L sub C is less or equal than 70 meters, okay? So for this roof, which the L sub C is equal to 18.75, which means less than 70, it means the C sub B is equal to 0.8. So guys, here is the trick. The C sub B is equal to 0.8 for a small roof. When do we call a roof a small roof? Whenever the L sub C is less than 70 meters, okay? And as I said, I'm going to convince you in a few minutes that L is C sub W, will use it as 1, okay? So in this equation you see right now, think about C sub W as 1 for now. One more time, last time. So C sub B, basic snow factor, equals to 0.8 for roof with L sub C less than 70 meters. If the characteristic length of the roof is more than 70 meters, and by the way, this is huge. If L sub C is more than 70 meters, then in this case, we don't use 0.8. We use the equation provided in II to estimate our C sub B. Now, before I continue, please take a note. And guys, to be honest, when I'm in class, I know how to teach. I know what to tell my students because I can see them. Over the last 6 years, I always ask my students to have like notes and write and have calculator and a ruler or something, right? To take good notes. And some of you may think that's not required right now. It's not required. You know, Tahir is presenting. We will have the slides as PDF. We will have the videos. But I'm telling you, really, the best is have some paper to take some notes. So please take a note. The L sub C will always between L and W. Always the L sub C will be in between L and W. Look at my example. So I gave you the L is equal to 820 and the W was 15 meter. The L sub C is 18.75, and you can see it is between L and W. It is somewhere, it's not an average, but it's somewhere kind of a geometrical average of your length and width of your building, of the roof, sorry, okay? So anytime you do calculations for L sub C and it is beyond the, like not in between L and W, you know that there is a mistake, okay? So always LC will be somewhere in between L and W. If you have a square roof, like a square roof, like 20 by 20, can you guess what will be the L sub C? If you have a roof and a square roof, so 20 by 20, can you guess what should be the L sub C without any calculations?
It's case 2.
What do you mean case 2? Like I'm saying that, okay, thank you, sir. So Merin, thank you. Again, the average, as I said, it will be always between L and W. It means if your roof is square, then the L sub C is simply 20 meter. And again, if you don't believe me, do it in the equation. So 2 times 20 minus 20 square over 20, you will see, you'll get 20. Okay, so for a square roof, L sub C will equal L and equal W. Okay, now guys, now I know, so let's focus next. So now we know for small roof, so any roof where LC is less than 70 meter, very simple, we use C sub B equal to 80% or 0.8. So how about if I design a building and when I estimate my L sub C more than 70, what can I do? What can I do? Look at this, please. So look at my screen. You will see the code provides some mathematical equation for LC more than 70 over CW square. As I said, cross CW square, it means LC more than 70. However, the equation is not really friendly, okay? I bet you if I ask all of you guys to work on this equation, I would say probably one of you guys will do it and the rest will do it a mistake, including myself, okay? So it's not really very friendly, and the way the code writes equation is not really friendly. So what happened is the code, you know, kind of they know about the equation is very difficult, and that's why they save your life, and then that's what they provide. So you can see here, and I want all of you guys to write on a note, and because I don't want any one of you in the exam or in the assignment to waste their time and simply solve this equation and find CB through the equation. If your LC is more than 70 meter, please write it down now. Do not cross this one out, cross it, okay? Because the code gives you an alternative way of estimating your CB. So the code on your behalf kind of substituted in the equation and give you a table format, which comes exactly from the same equation. So the table format is happening on the next page here, and simply the first column is the L sub C multiplied by C squared W. Please, again, think about that C sub W always is 1, always. Again, in a few minutes, I'll convince you. So when you think about C sub W is equal to 1, it means this column is simply your L sub C, L sub C. And then now, if you want to find the C sub B, look at this. So if L sub C equal to 70, you go horizontal. For CW equal to 1, you can see the number is here is equal to 0.8. One more time. If the LC, which is characteristic length of your roof, equal to 70 meter, then you go horizontal, and then you meet the column where C sub W is equal to 1, because I'm gonna show you that we are not able to use 0.5 or 75, okay, percent. So this is the column that we will always use, first column only, where C sub W is equal to 1. You can see for 70, we get our 0.8, okay? Where is 0.8? It's here. When C sub B, the LC is anywhere less than 70, we use 0.8, okay? Now, as the L sub C grows more than 70, you can see what happens to the C sub B. We get 82%, 85%, all the way to one when the L sub C is 440. 440. Guys, so you know, L sub C 440, I think it will never happen probably once in the history. In the history. Like, for example, I think Apple, they built like a huge monster building for them in the States, and it's a big ring, and in this case, probably yes. But it means your building is half kilometer, 440 meters. It means it's almost 500 meters. So if you're building the L sub C is half kilometer by half kilometer, 500 meter by 500 meter. In this case, we get C sub B equal to 1. It means my ground snow is the roof snow. Okay, are you following so far? I want to get some feedback quickly so I know my base. Are you guys following so far? Thermometer, check. Okay, so guys, again, let's summarize CB. Thank you, sir. Okay, so let's summarize CB one more time. So CB is very simple. It's a basic snow factor. It depends on the size of your roof. When I say the size, it is not the L, it is not the W. It is somewhere in between, called L sub C, characteristic length of the roof. If this L sub C is less than 70, very simple, which happens for most of the structure, we use 80%, 0.8. If the L sub C exceeds 70 meter, please do not use the equation. There is another way, which comes from the same equation, but in a simpler, it just takes a few seconds. If you try to use the equation, it will take you forever in the exam or in the assignment, okay? So in the table, very simple. Once you find the L sub C, you go on the first column, and then you turn right. I know some of you will say, Tahir, listen, the columns, it has interval, so it goes from 70 to 80, 80 to 100, 120. So it's not really continuous. It is estimated at very specific value for L sub C. Now, what if my L sub C is equal to 90? What do you think? Any help? Show your hands, please, if you know the answer. If L sub C is equal to 90, what can I do? Let's go with Hariwander.
Just take the average between 80 and 100.
Michael?
Take the average.
Okay, guys, so I'm going to give you both for Hariwander and Michael, I'm going to give you a couple of marks. Thank you so much. But you know, the average is true only for what are the numbers I said, because simply 90 is in the middle between 80 and 100, which means to find the value, I need to say 0.82 plus 0.85 divided by 2. So an average between 82% and 85%. Okay. However, the right word is interpolation. So thank you so much, Michael, for that. So you will get a couple of marks more. So Michael. Okay. So you can see the right wording. It's supposed to say interpolate. So we do interpolation, and it's a linear interpolation, because if you study math somewhere, you will see interpolation is a huge topic, and it can be linear or bilinear or something like that. We do linear interpolation. So we interpolate in between the values. For example, if I have 85 meter, the L sub C, it will not be the average between 0.82 and 0.85. I just have to do a linear interpolation. Okay. If you don't know how to do linear interpolation, you need to find this from the internet. And if you cannot, come see me. Okay. Linear interpolation. That's the name. Thank you. Okay. Now, it is time to discuss the C sub W. And I kept saying for 100 times, I said, I'm going to convince you that the C sub W is equal to 1. So let's begin. So guys, C sub W is a wind factor. Guys, I know that it's 152 and probably you're bored by now. So I'm going to break straight after C sub W. So C sub W, it's called wind exposure factor. Wind exposure factor. We're talking about snow. So what's the business of the wind right now? Huh? We keep saying we're estimating snow load. So has the wind any business in the snow estimation? Yes, it does. Because simply the wind it can simply blow off your snow off the roof, which means it can potentially reduce the snow accumulation. One more time, it is called wind exposure, and it is affecting the snow load, because if the roof is exposed to the wind can blow some of the snow and you get less snow on the roof. Now, what happened here, guys, is that the code asks us to read statement number 3, number 4. So statement number 3, it says except as provided. And we agree, as soon as you hit the word except, it means there's an exception. You have to stop and then go to where you have exception. So it says except as provided in sentence number 4. Okay, so it's time to read number 4. So what happened here is in number 4, it says for buildings in low and normal importance. Buildings in low and normal importance. So which means I can do that for my house. I can do that for agricultural building for animals or hay barn. Then what can you do? Wind exposure factor. So I'm going to skip this one for easier reading. So for buildings in category low and normal importance, the wind exposure factor C sub W given in sentence number 3 may be reduced. It means less than 1. It means we can simply take a little bit of the snow load. Okay. For 75% for rural area or 50% for exposed area north of tree line. And then it puts a lot of condition. Okay. A lot of condition. The building is exposed in all sides to the wind. Guys, I'm not going to really waste my time, and I will tell you and I will prove for you why I'm not really interested to read this. Guys, listen, the thing here is you're saying my wind is going to blow some of the snow when the roof is exposed. And what's that mean? It means my roof has to be exposed. Okay? So I'm going to give you kind of a scenario. I'm a designer. Tahir is a designer. Somebody hired me to design a house, and this house in a new community, very little. So yes, in this case, when I design, for the moment I design, you know, there are nothing. So probably the wind, yes, will blow some of the snow. Now I'm asking you, should I make the owner promise me that no one ever build or maybe plant a tree around the house? Because look at this. Once you plant some trees around the house, it creates a barrier for the wind, and simply the wind cannot blow the snow off the roof. I don't think this is kind of realistic. When we design the house, we shouldn't be so optimistic like this. Like, you know, take a promise from the owner, please don't never plant a tree, or you know, nobody else around you will build a house to kind of reduce the wind effect. It's not really realistic. And I would say on the safer side is to simply do not reduce the snow because of the wind, because there is no guarantee that this is going to stay and happen for the next 50 years, which is the lifespan of your structure. Okay. So guys, conclusion is, because simply we cannot really, the statement number 4 has lots of requirement to reduce the snow by 50% or 75%, I would say it's unsafe. Myself will always use statement number 4, number 3, and it says here the wind exposure C sub W shall be 1. Guys, the meaning of 1 has a meaning. It means do not. When you say 1, it means 100%. It means do not reduce the snow because of the wind. So please, in my class going forward, we always think about C sub W as 1. Because in order for us to reduce and take advantage of statement number 4, so many things has to happen. It has to be low importance or normal. Fine, lots of them. Houses, warehouses, office building, but also read below in A and B and C, you will see there are lots of kind of restrictions when you apply the reduction of 50% or 75%. So don't go there. Always C sub W equal to 1. And guys, now it's time for a good break. Okay. So I'm going to ask for questions first before we go for a break. and then we can take back 10 minutes. One thing also to notice is that C sub W is unitless. All the factors are unitless except two, which is SS and S sub R. Those are load intensity in kVA. Everything else is unitless. Any question? If you have any question, show your hands, please. Show your hands if you have any question, please. Okay, looks like there's nothing, so I'm gonna see you guys back here at 2:08, 10 minutes from now. Thank you.